Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is the theory of ideals in fields. Okay, so initially what we're going to do is talk about the fact that there are only ever two ideals in a field, and those are the zero ideal and the unit ideal, which are present in any ring, which any field certainly is. Then what we're going to talk about is the fact that if we look at the polynomial ring over a field, then the ideals in that polynomial ring over the field are all principal ideals. There are no ideals that are not principal ideals. Okay, and we'll prove that in the second part of this video. Okay, but firstly then, let's just have a look at ideals in a field. Okay, so initially then, let me just remind you of what an ideal is. So an ideal, first and foremost, is a subset of a ring. Okay, now fields are all rings, but we'll start off just with a general ring here. So an ideal is a subset of a ring. Okay, and let me just draw a picture to show this. So if we have this box here representing our ring, okay, then we'll have this subset of the box representing our ideal here. So this subset will be our ideal. Now, to be an ideal, to qualify as an ideal, a subset has to obey a bunch of criteria which make it special. And those two criteria are, firstly, that it needs to be an additive subgroup. So let me put these down here. So criterion number one is that I must be an additive subgroup. So I'll put this like so. I must be a subgroup of the ring capital R. Now, because addition on the ring is an abelian group operation, then of course this additive subgroup will be a normal subgroup, because all subgroups in an abelian group are normal subgroups. Okay, so criterion number one is that it must be an additive subgroup, so it must be closed under addition, it must obey associativity, which will be trivial, it must have the additive identity in there, and finally it must have additive inverses in there, and it will also obey commutativity because it will inherit that from the addition on the larger ring. Okay, so it needs to be an additive subgroup, so I'll just put additive here. Okay. In addition, it needs to be closed under multiplication. So that's criterion number one, an additive subgroup. Criterion number two is that it must be closed under multiplication. Now, I'll stress again, ideals are not necessarily subrings. Okay? They don't necessarily need to contain the multiplicative identity of the larger ring. What they do need to be, however, is they need to be closed under multiplication. Okay, so let me write this out. So whatever element of the ideal you pick, for all A is an element of the ideal capital I, and whatever element of the larger ring you pick, capital little r here, so let's just add this on our picture. So I've got some little a from the ideal, so I'll colour that one in green here, and I've got some little r from the larger ring here, and we'll colour things to do with the larger ring in red. So here I'll outline the larger ring in red here, and little r of course could be from the ideal, it's just an arbitrary element of our larger ring capital R. Then it must be the case that if we multiply these two together, so r times a in the ring, that answer must also be in the ideal, and it must also be true if you do it the other way round. So note, I haven't yet demanded that this ring is a commutative ring. Okay, so r times a could be different from a times r, so we'll also demand that a times r is an element of the ideal. Now of course, if we're working with a commutative ring, which we often are, then these two elements will be exactly the same, so we don't need to write those two statements separately. But if we're working in a non-commutative ring or a general ring, we do need to put these two statements separately. So if you take any element of the ideal and multiply it by any element of the ring, the answer you get must be another element of the ideal. The ideal must be closed under multiplication by the larger ring. Okay, and those are the two criteria then that an ideal must obey. Okay, so what we're now going to do is have a look at ideals in a field. Now remember, a field is a very special ring. Firstly, it's a commutative ring, so we're now working in a field which we'll call capital F. So firstly, remember that a field is a commutative ring, but it also obeys an additional axiom, and the additional axiom is that a field is closed under multiplicative inverses except for the additive identity. So a field has a multiplicative inverse for all elements other than the additive identity, so I'll add this on here. So for all, let's say little x is an element of the field except the additive identity. So pick whatever element you like from the field except the additive identity, so you can't pick 0. It must be the case that there exists, so there must exist a unique multiplicative inverse, and the multiplicative inverse is going to be unique because if you had multiple multiplicative inverses, you could prove that that would break distributivity, sorry, not distributivity, associativity. It would break associativity because quite simply you could put x in the middle and then the two multiplicative inverses on either side, and then if you consider the two ways that you can put the brackets, you'll end up with different answers and therefore associativity would be broken. Okay, so there must exist a unique multiplicative inverse which we call 1 over x, or x to the power of -1, which is an element of the field. So there must exist another symbol in the field which we call 1 over x, or x to the -1, or the multiplicative inverse of x, such that the two of them multiply together. So x times 1 over x is equal to the multiplicative identity, and I don't need to worry about putting it both ways round because of course I've assumed that this is a commutative ring, so it doesn't matter because either way you multiply them round you'll get the same answer. So x times 1 over x must equal 1. So for all elements apart from the additive identity there must exist a multiplicative inverse. So these are very special rings. Now because they are rings, they do obey all the axioms of ring theory, we can think about what are the ideals in a field. And the first theorem I want to prove then is that there are only two ideals in a field. Okay? So this is where the real stuff starts now. So theorem number 1, I claim that the only two ideals of a field are the 0 ideal, so the principal ideal generated by 0, which is the ideal that just contains 0, because of course in the video, and the previous video in this based on ring theory where we discussed ideals for the first time, we saw that the definition of a principal ideal is one where you take this element here which you're using to generate the principal ideal and multiply it by every other element of the ring, collect all those answers together, and that's going to be your subset, and we prove that that's always an ideal of your ring. Okay, now if you generate the principal ideal for 0, of course you're just going to multiply all the elements of the ring by 0. And of course when you multiply all the elements of the ring by 0, you'll just get 0 back again. So this is just the subset that contains the single element, which is the additive identity. Okay, so this is the 0 ideal. Now that's certainly a subset of any ring, and it will in fact be an ideal. It will satisfy these two criteria, that it's an additive subgroup, and that any element of the ring multiplied by it gives an element back in here. Okay, so that's one of them. And then the other one is the unit ideal, which is the principal ideal generated by 1, and that's equal to the entire ring, because of course when you just multiply all the elements of the ring by 1, you get back all the elements of the ring. So I claim then that these are the only two ideals of a field, the subset that contains just the additive identity in the field and the entire field again. Those are the only two ideals, the two trivial ideals, the ideals that are there no matter what ring you're talking about. Okay, so I claim there are no proper ideals in a field. So how am I going to prove this? Well, let's take an ideal. Let's say we have an ideal which is an ideal of our field. In the way that some people sometimes denote I as an ideal of a ring is to put the same symbols you would use for normal subgroup here. Okay, it's not completely standard notation, but it is the most standard notation for I as an ideal of a ring. Okay, so let's say I is an ideal of the field. So there are two possibilities. One possibility is that the ideal is equal to the 0 ideal. So this ideal could be the 0 ideal here. Okay? The other possibility is that the ideal then has to contain an element other than 0. So if the ideal is not the 0 ideal, then the ideal must have to contain 0 and something else, at least one other element of the field. Okay, now all ideals always contain the additive identity, because remember they're additive subgroups, and additive subgroups always must contain the additive identity. Okay, but if it's not just going to be the zero ideal, then it must contain something other than the additive identity as well, otherwise it would just be the zero ideal. Okay, and that might contain a lot else as well, but I only need one of these elements here. Okay, one other element in the ideal that is not equal to the additive identity. So nothing fancy yet, I've just said that either it's just the set that contains the zero element, or it's a larger set and therefore it has to contain an element that is not equal to zero. Very basic so far. Now, I claim that I can instantly conclude then that this is equal to the entire field. So I can instantly conclude that this is equal to the entire field, and the reason is that if you contain an element that is not equal to the additive identity in the field, then this element, because we're working in a field, will have a multiplicative inverse. Okay, so there will exist in the field 1 over x here. Okay, so that's perfectly fine. We're working in a field, so all non-additive identity elements do indeed have a multiplicative inverse. So this particular element that I've got here, x, which is this non-zero element in my ideal, it will have a multiplicative inverse in the field. Now, the ideal, remember, has to be closed under multiplication. Okay, so it must be the case that if I multiply an element of the ideal by any element of the larger field, that I get something that's back in the ideal. Therefore, 1 over x times x, which is exactly this, something of this form. X is from my ideal, 1 over x is from my larger field in this case, but of course it is a ring. That has to be an element of the ideal, but of course the answer here is going to be 1. So that instantly now tells me that 1 has to be an element of my ideal. And this is a catastrophe, because the instant 1 is in your ideal, you have to have the entire field in your ideal, because remember, now what we can say is, okay, because the ideal has to be closed under multiplication, it has to be the case that if I take any element of the field, I'll call it little r here, and multiply that by 1, that has to be an element of the ideal. Okay, I'm just saying, okay, if I take any element of the field, multiply it by 1, that has to be an element of the ideal, because 1's an element of the ideal. But of course, r times 1 is just r, so that now says that any element of the field has to be an element of the ideal. So the instant you have 1 in an ideal, you have to have every other element of the ring in that ideal. And that's how we have now proven that this ideal must be equal to the entire field. So the instant you have an element that is not the additive identity in your ideal, then it instantly becomes the case that it has to be equal to the entire field. If you're working in a field, this isn't true if you're working in a ring, because if you're working in a ring, it isn't necessarily true that the multiplicative inverse of x exists. So this step doesn't work here. It isn't then instantly obvious that 1 has to be in the ideal. Okay, but it does hold true in any ring that the instant you have 1 in the ideal, the entire ring has to be in the ideal. What doesn't work in an arbitrary ring is that you would ever go from just having a non-additive identity element being in the ring to having from having a non-additive identity element in your ideal to having 1 in your ideal. Okay, so there's the proof then that any field only has 2 ideals. It has the zero ideal and then the unit ideal, which is the entire field. Okay, so a very simple ideal structure for a field. Now what we want to do is go the other way around. I want to show that if I have some ring here, so let's say I have some ring, okay, and it only has 2 ideals. So let's say it only has the zero ideal and the unit ideal. So let's say this ring is very special because it only has 2 ideals. These are the only 2 ideals. There are no other ideals. I claim that I can instantly conclude that this ring is a field. Okay, so I want to prove that this is a way of characterizing fields. If you have a ring that has only 2 ideals, you can instantly conclude it's a field. If you have a field, you can instantly conclude it has only 2 ideals. It works both ways around. Okay, it's an if and only if. There are 2 equivalent ways of characterizing this algebraic structure. Okay, right. So how am I going to prove this? So what do I need to prove? Oh, and I should say we're beginning with a commutative ring. Okay, so let's say we have a commutative ring here that has only 2 ideals, the zero ideal and the 1 ideal. What I now want to prove then is that it is in fact a field. So all I need to prove is the final criterion. All I need to prove is the final step, that every single element of this ring is going to have a multiplicative inverse. Okay, apart from the additive identity. So what I need to prove then, so let's take an arbitrary x that is an element of the ring which is not the additive identity. So what I want to show is that this is going to have a multiplicative inverse. Now how can I do this? Well, quite simply, I can consider the principal ideal generated by x. Okay, so consider this thing. Now, x is not equal to the additive identity, and x must always be an element of its own principal ideal, because of course you can multiply x by 1 when you're generating this principal ideal, and that will give you x. So it cannot be equal to the 0 ideal is my point here. This principal ideal generated by x, where x is not the additive identity, is not going to be the 0 ideal. But it will be an ideal, and therefore there's only one possibility for what this ideal is going to be equal to. It's going to be the unit ideal. So whatever x you take that is not the additive identity in your ring, the principal ideal generated by it must be equal to the unit ideal in your ring now, when you're saying that there are only those two ideals, the 0 ideal and the unit ideal. Okay, now, if you're equal to the unit ideal, then you're equal to the entire ring. Okay, so this means that this principal ideal generated by x is the entire ring. Now let's spell that out a little bit more, because what is the principal ideal generated by x? It's just all elements of the ring multiplied by x. So you go through absolutely every single element of the ring, you multiply it by x, collect all the answers together, stick them into a great big set. That's what is meant by the principal ideal generated by x. And I'm now saying that this as a set is equal to the entire ring. So in particular, some element in this is equal to 1, and that means that some element of the ring multiplied by x gave me 1. Otherwise 1 would not be in the principal ideal generated by x. Okay, so there must exist some r, which is an element of capital R, such that r times x is equal to 1, otherwise 1 would not have been in the principal ideal generated by x, and we know it has to be, because 1 is an element of the ring, and the principal ideal generated by x is equal to the entire ring. So of course this element of the ring which we multiply by x to give 1, that will be the multiplicative inverse of x. That will be 1 over x. So I have found you a multiplicative inverse for x, and this argument holds up no matter what x you picked from the ring which was not the additive identity. So if you've got a commutative ring which has only two ideals, the 0 ideal and the unit ideal, then you can instantly conclude that that is a field, that there are going to be multiplicative inverses in that ring for every element other than the additive identity element. Okay, so we'll have a break there, and in the next video what we'll discuss is the ideals of a polynomial ring over a field.